Good afternoon, everyone. So we will continue with the next section. As you understand that we have covered magnetic field, a great deal of concepts in that, particularly how to define magnetic field, detail about Biot-Savart law, then Ampere's law, and vector potential, and other properties of the magnetic field. And we would continue with the magnetic induction now. We have discussed about Faraday's law and Lenge's law, how these things are defined. We'll get some idea about self-inductance and mutual inductance, here reciprocity theorem, and further get into Maxwell's equation. I'll take a minute on some of the basics of electrodynamics. We all know about Ohm's law. It's a standard concept now. So basically, for most of the substances, the current density, which is defined by J, which is a vector quantity, is generally proportional to the force per unit charge. Now, this constant is called conductivity, and the reciprocal of that is resistivity. Now, in principle, the force that drives the charge to produce the current could be anything, chemical, gravitational, or anything. But here in electromagnetic force can be defined in terms of E plus V cross B. We know that already from the initial chapter. So the current density can be defined in this manner. For velocities, for charges with a very small velocity, the last term will become very small. So we'll basically have an equation which is much more simpler and dependent on the electric field. That brings us to a simple example of a cylindrical resistor of cross-sectional area A and a length L, made from material with a conductivity S. We can very easily calculate the current, which is area into the current density. And that comes in terms of voltage, because we know that the electric field is basically voltage by length. With this example, we can understand the total current flowing from one electrode to the other is proportional to the potential difference between them. And that gives us the age-old P equals to IR, whereas R is the resistance, and it basically is a unit of ohms. For steady and uniform current, because the divergence of E will actually become 0 from the earlier equation. Another which is important, we all know about the Joule heating law, which is I square R. Now we'll deal with electromagnetic induction here and Faraday's law. We have already discussed much of it in the last chapter in detail. So I'll go briefly on this one and try to focus on something more advanced. So the electromotive force is equal to the negative, which is reverse of d psi by dt, which is changing magnetic field induces an electric field that we know from Faraday's law. And the electromagnetic force EMF can be also defined in terms of a closed line integral of electric field or dl. And that gives us the integral form of Faraday's law. So this thing, which is E dot dl equals minus of integral of delta B by delta T to dA. So the delta B into delta A, that is coming from d psi, is converted. So that's the flux is converted into area, a small area with the small function of field in that area. And that's the integral form of Faraday's law. We can convert that in terms of differential form with a Stokes theorem, which is curl E equals to minus of delta B by delta T. Now Faraday's law reduces to the old rule, which is E dot dl equals 0 if it's a closed loop of equation. In terms of differential form, it will be basically curl of E equals to 0. Now, in simple, Faraday's discovery tells us that there is really two distinct kind of electric field. We have discussed about that in the previous lecture also. These attributed directly to electric charges. And another one associated with changing magnetic field. We know the one we discussed before, the electric field, which is defined largely by Coulomb's law and all that. We have discussed a great deal of that in electrostatic. That's conservative. While the one we are having here that is associated with the changing of magnetic field, that is non-conservative. So the former can be calculated in static case using Coulomb's law. The later can be found by exploiting the analogy between Faraday's law. So these are the equations which are important. And then we have Ampere's law, which is curl of B equals to mu 0 and J. Of course, the curl alone is not sufficient to determine a field. You must also specify the divergence. But as long as E is pure, Faraday's field, due to exclusively to the changing of B, Gauss's law says that the divergence of E is 0. While the magnetic field, of course, will be the divergence of B equals to 0 too. So, in simple, you can conclude that the Faraday-induced electric field are determined by the rate of change of B, which is magnetic field, time, in exactly the same way as magnetostatic fields are determined by mu 0 J. In particular, if symmetry permits, we can use this tricks associated with Ampere's law in integral form. So the Ampere's law, which is the cross product of delta and B equals to mu 0 J, can be also put into form of integral, which is mu the closed integral of B dot dl equals to mu 0 I enclosed. Now, we have discussed most of it in last lecture, so I'll not go into much of the detail of how to come to these points. Now, the Faraday's law can be also put into integral form, as I mentioned. The rate of change of magnetic field flux through the Amperean loop plays the role formerly assigned to mu 0 I enclosed. Now, a uniform magnetic field, so this is an example pointing straight up, it's a shaded area. If B is changing with time, what is the induced electric field? So we can just get it from simple Faraday's law equation. And you can actually use Ampere's law and calculate the electric field in that. Now, inductance. In case of when you have two loops of wire, if you run a steady current I1 around loop 1, it produces a magnetic field B1. Some of the field lines pass through the loop 2. And if the flux P side 2, the flux of P1 through 2, you may have a tough time actually calculating B1. At a glance from Biot-Savart law, so from Biot-Savart law, you can calculate, because we have already figured out this equation for like if you have a current carrying loop, how much will be the field because of that at a distance r. This will be this expression, and is proportional to the current I1. Therefore, the flux through loop 2 will be also proportional to the current I1. So if we do the like line integration across the area of 2, then that will be B1, which is the field, and the surface integration will be dA2. And you understand that, as I mentioned, that the psi 2, which is the flux in the second loop, is proportional to the I1, which is the current in loop 1, then you have a proportionality constant in the middle. This M21, which is the constant of proportionality, is known as the mutual inductance of the two fluids. Mutual inductance is the important concept that we're introducing now. Now, this can further give you another mathematical expression by actually converting the B1, which is the field, in terms of vector potential, which is A1. So the B1 would be the cross product of A1. And from Stokes' theorem, you can just simply have a closed loop integration over the dL2 of A1. Now, A1 from earlier, we figured out that the vector potential can be calculated like this. So if you put that value, then from the equation on the top for the mutual inductance, where we introduce mutual inductance, which is proportional, the flux is proportional to the current I1, if you put that, then you find out the Newman's formula, which is the double integration, one integration around loop 1, another in loop 2. And this can be used to calculate the mutual inductance in this kind of a case. Now you can already understand from this equation that this M21 is purely a geometrical quantity having to do with size, shape, and relative positions of the two loops. Now from this equation of that is also, you can see that it's unchanged if we switch the loops from 1 to 2. So that means that M21 will be same as M12. So the mutual inductance in vice versa will be always same. So that brings us to a conclusion whether the shapes of the positions of the loops, the flux through 2 when we turn a current I around 1 is identical to the flux through 1 when we send the same current I around 2. We may as well drop the subscript and call them both M. So this is a fine example of a short solenoid of length L, radius A, with turns N1 per unit length, lies on the axis of very long solenoid, radius B, N2 turns per unit length, and current I flows in the short solenoid. What is the flux to the long solenoid? Then we can calculate it because we know the field for solenoid. We have calculated that before. And from that, the previous equation, as we know that the flux for a current I in short solenoid would put through the long one, which is what we set out to find. Incidentally, the mutual inductance in this case would be proportional to the current. So this would be calculated from this one. Now, in case of the first example, when we were introducing this one, the flux to loop 2, I mean, like if we vary the current in loop 1, the flux to loop 2 will vary accordingly. Now, Faraday's law says that this changing of flux will induce an EMF in loop 2. So we have the EMF in loop 2 equals to the variation of the flux with time. And from earlier equation, we can understand that this would be mdi1 by dt. And this, from this also we can conclude that every time you change the current in loop 1, an induced current flows in loop 2, even though there is no wires connecting with each other. That's because of induction. Now, a changing current not only induces an EMF in any nearby loop, it also induces an EMF in the source loop itself. This is an important concept. It's called self-inductance. Once again, the field, also the flux is proportional to the current. So psi will be this time L into I, where L is the self-inductance, which is the proportionality constant in this case. As with M, which is the mutual conductance, it depends on the geometry, size, and shape of the loop. If the current changes, the EMF induced in the loop is the, as we figured from the top, it will be L minus of L di by dt. The inductance is measured in henries. Henry is a volt second per ampere. So if we do another mathematical problem where we have self-inductance of a toroidal coil with rectangular cross section in a radius A, outer radius B, and height h, which carries a total of n turns. Then we know the magnetic field inside the toroid, and from these equations that we did earlier, we can actually calculate the self-inductance from this one. Now, an important aspect is like inductance, like capacitance, is an intrinsically positive quantity. From Lenge's law, which is enforced by the minus sign, dictates that the EMF is in such a direction as to oppose any change in current. For this reason, it is called a back EMF. However, you try to alter the current in the wire, you must fight against this back EMF. Thus, the inductance plays somewhat the same role in the electric circuit that mass plays in mechanical system. The greater L, which is the self-inductance, the harder it is to change the current. Just as the larger the mass, the harder it would be to change the object's velocity. Now we also have to calculate the magnetic field that is stored. You can understand that there is sort of a resistance used because of this property. So naturally that requires some amount of work, and that work to build up that current, and that work is actually stored as energy in the system. So it takes a certain amount of energy to start a current flowing in a circuit. It's not the energy that is delivered to the resistor or the converted into heat. It is basically lost as far as the circuit is concerned, and can be large or small depending on how long you let the circuit current run. What we're talking about here is the work you must do against the back EMF to get the current going, which we discussed in the last slide. This is a fixed amount and it's recoverable. You can get it back when the current is turned off. In the meantime, it represents energy latent in the circuit, as you will see in the moment. It can be regarded as the energy stored in the magnetic field. The work done on the unit chain charge against the back EMF in the trip around the circuit is this, which is basically the negative of EMF. The minus sign records the fact that the work done by U is against EMF, not work done by the EMF. Now the amount of charge per unit time passing around the wire is I. So that the total work done per unit time means like you have to do a dt will be this, which is Li di by dt. If we start with zero current and build it up from finally I, then you have to do an integration from 0 to I. And this gives you half Li square. Now, it does not depend on how long it takes to actually take the current from 0 to 1. Only it depends on the geometry of the loop, which is what the L depends on, and the final current I. There is another way to write the work done, which will be stored as energy, which has the advantage of readily like generalize the surface and volume elements, volume currents, if we do it in terms of flux. So as we understand that flux will be same as the surface integration across the surface, it's closing with P dot dA, and we can take a curl of A and then convert it from Stokes' law to a line integral. So this gives us with the proportionality L to I equal to this closed integration, line integration across A dot dA. And from that, we can also write it in terms of volume, in terms of line integration, it will be half of A dot I dot dl. And you can convert it in terms of volume charge integration when we do it in terms of volume. Now with some more mathematics by using Ampere's law in the middle, you can actually convert this in terms of B. I mean, now like you can introduce the terminology B also by parts. I mean, like we have to just integrate by parts and enabling us to move the derivative from A to B to A. And we can have this nice form of the work done, where this S is the surface bounded by the volume V. So you have a volume term and you have a surface term. Now, you have to note that the entire volume occupied by the current is described here. But any region longer than this will do just as well. I mean, like if there is a larger area also, then you can also consider that, because J will be 0 outside that. In case if we like integrate all over the space, then the space in surface integration will be basically 0, and you will have something like this kind of equation. And with some of this, I mean, some particular cases, you can have a rather more simpler equation than this complicated one. Particularly for a point in which it's producing a magnetic field where previously there was no, nothing. Then requires changing the field, and changing a B field according to the Faraday's produces an electric field. The electric field can actually do some work which magnetic field would not do. In the beginning, there is no electric field. At the end, there is no electric field. But in between, while the B is building up, there is an electric field. And that is where the work is done. Switch over to Maxwell's equation. Now, as we understand till now, what we have studied is there are four equations in electrodynamics, which are Gauss's law, and there is one more which is almost relatable to Gauss's law, Faraday's law, and Ampere's law. Now, in case we take a divergence of the Faraday's law, which is 3, and we do some calculation, you see the left side is 0 because of the divergence of the curl is 0. The right side is 0 by the virtue of equation 2, which is the divergence of B equals to 0. But when you do the same thing, number 4, which is the Ampere's law, you don't see that it is actually the left side is 0, while the right side is not. For steady current, the divergence of J is 0, but eventually when we go beyond magnetostatics, Ampere's law cannot be right. So the question here is, for Ampere's law, when we try to do the same operation in both sides, we see that well, the left side is going to 0, the right side is not going to 0. It's because of this one term, which is J. Now, there is another way to see Ampere's law is bound to fail in non-steady current. So while it's a steady current, Ampere's law holds well. But if it's not a steady current, a non-steady current, then it will fail. If we have a process of charging up a capacitor, then from Ampere's law, we see the closed integral across this B dot dl, which is the field built up, equals to mu 0 I enclosed. Now, if we apply this Amperean loop shown in the diagram, then to determine the I enclosed, which is like the total current passing through the loop, or more precisely, the current that is tracing a surface that has a loop for its boundary. In this case, the simplest surface lies on the plane of the loop. A wire punctures this loop. So I enclosed will be which is the current flowing through the circuit. But if we draw a balloon-shaped surface, then no current passes through this. Because in the middle, there is nothing, there is a hollow. And in this case, the I enclosed will be 0. So if you change the surface from 1 to 2, you can see that now the I enclosed will be 0. We never had this problem in electromagnetics because the conflict arises only when the charge is piling somewhere. In this case, on a capacitor plate. But for non-steady current, such as this one, the current enclosed by the loop is an ill-defined notion, since it depends entirely on the surface you use. So to fix this one, Ampere came up with this concept. that we can already understand that this equation, the right hand side needs to be 0. I mean the term which has J, and we don't have a steady current, we have a non-steady current. If we use the continuity equation and Gauss's law, we can change this equation differently. And then this equation becomes something like this, which is curl of B equals to mu 0 J plus mu 0 epsilon 0 delta E by delta T. So here, basically the extra term we're adding with J. Now, this modification will not change anything. As far as magnetostatics is concerned, when the E is constant, we still have the curl of B equals to mu 0 J. Because when you do this equation, this term will actually cancel out. In fact, Maxwell's term is hard to detect in ordinary electromagnetic experiment, where it must compete for recognition with J. That's where Faraday and others never discovered it in the laboratory. However, it plays a crucial role in the propagation of electromagnetic wave, as we would see in a later chapter. Apart from carrying the defect in Ampere's law, Maxwell term has a certain aesthetic appeal. Just as changing the magnetic field induced an electric field, a changing magnetic field induces a magnetic field. A changing electric field induces a magnetic field. So we also prove that while this one is actually, while you're changing a magnetic field, which is delta E by delta T, it gives rise to a magnetic field. The real confirmation of Maxwell's theory came many years later in 1888 by Hertz's experiment on electromagnetic waves. Meanwhile, Maxwell called his extra term as displacement current. So curl of B equals to mu 0 J plus this mu 0 epsilon delta E by delta T becomes your new Ampere's law. And the extra term, which is JD, is displacement current, which is epsilon delta E by delta T. And that saves this equation. And the name is misleading because this term has nothing to do with current except that it adds up to J in Ampere's law. Now, displacement current resolves the paradox of charging capacitor, which we were discussing earlier. If the capacitor plates are very close together, but the calculation is simpler if you assume this, then the electric field between them will be, as we know, because of the electric field from electrostatics we studied earlier, which is Q by A by epsilon. Q is the charge in plate A, which is the area, and that can be converted in terms of when we do the time derivative with this one, delta E by delta T, finally gives you I by epsilon A. Now the integral form of this one, if we do, then we automatically find that the closed integration of B dot dl equals to mu 0 I enclosed plus mu 0 epsilon 0 to delta E by delta T into delta. And it's a surface integration across the surface, which is delta A. Now, in case you choose the flat surface, then E equals to 0. So I enclosed will be I. If on the other side you use the balloon set surface, then I enclosed will be 0, but delta E by delta T on that surface will be I by epsilon. So we get the same answer for either surface, though the first case it comes from the genuine current and the second one it comes from the displacement current. So finally, the Maxwell's equation comes down to divergence of E equals to 1 by epsilon, which is basically the rho by epsilon 0. That's the Gauss's law in derivative form, differential form. Divergence of B equals to 0. Don't have a name of that. The Faraday's law, which is curl of E equals to minus of delta B by delta T. And we have the Ampere's law with the correction by Maxwell. And if we include the forces law, which is F equals to E Q into E plus P cross B, this will summarize the entire theoretical content of classical electrodynamics. We can also have the continuity equation, which is also important, which is divergence of J equals to minus of delta rho by delta T. This is the mathematical expression of conservation of charge and can be driven from Maxwell's equation by applying divergence to number 4. Now here we have written the Maxwell's equation in a traditional way, which emphasizes that they specify the divergence and curl of E and B. In this form, they reinforce the notion that the electric field can be reduced either by change of rho or by changing magnetic field, which is delta P by delta T. And magnetic fields can be produced either by current, which is J, or by changing electric field, which is delta E by delta T. Actually, this is somewhat misleading because when you come right down, like delta B by delta T and delta E by delta T, they are themselves due to the charges and the current. So we can write it in another form also. Basically, it's the same thing. With the fields E and B on the left and the sources rho and J on the right, this notation emphasizes that all electromagnetic fields are ultimately attributed to the charges and currents. Maxwell's equation tell you how charges produce fields. Reciprocally, the force law tells you how fields affect charges.